Hi, this is Dr. Habib Ahmed. I welcome you to my YouTube channel. In this video, I will introduce you to SCAPS 1D, a powerful simulation software tool developed for simulating the performance of solar cells. SCAPS 1D stands for Semiconductor Capacitance Simulator in One Dimension. It has been a cornerstone in the field of photovoltaics since its inception. Originating from research conducted at the University of Ghent in Belgium, SCAPS 1D was developed to provide researchers, engineers, and students with a robust platform for studying and optimizing solar cell designs. It offers essential capabilities for analyzing key parameters such as current voltage characteristics, quantum efficiency, absorption, and much more. Throughout this tutorial, with the help of a silicon solar cell example, we will cover an overview of SCAPS 1D software and its key features, how to set up simulation and input its parameters, analyzing results such as current voltage characteristics, quantum efficiency, and much more. And I'm also going to give you tips and tricks for getting the most out of your simulation. So let me give you a slight background as well. So basically, here is my YouTube channel. The handle of my YouTube channel is @Habib Ahmed Gardik. So on this channel previously, I've posted a video on the theory of silicon solar cells. And similarly, if you have followed my channel, you might already know that I have performed a lot of simulation stuff of various kind of devices using Silvaco TCAD software, Silvaco technology computer aided design software. So in one of the videos that I previously posted, it's this one, I demonstrated how to perform the Silvaco TCAD simulation of silicon, gallium nitride, and gallium arsenide solar cells. And inside that simulation, talking about the silicon solar cell part, I basically worked on silicon PIN solar cells. I simulated 3 different structures. A silicon PIN solar cell with eye layer thickness of 10 micrometers. Another silicon PIN solar cell with eye layer thickness of 20 micrometer, and similarly a third one with eye layer thickness of 50 micrometers. So here is the code, Silvaco TCAD simulation code for the 10 micrometers PIN solar cell. I've kept the P-type doping and the N-type doping of the top and bottom layer to 5 into 10 to the power of 18 per centimeter cube. Similarly, I've kept the eye layer doping at 1 into 10 to the power of 14 per centimeter cube. So I'm going to perform the simulation of the same structures using SCAPS 1D software so that we can have a comparison of the simulation of silicon PIN solar cell using SCAPS 1D and also Silvaco TCAD. And then I will show you a slight comparison of the two softwares as well. So whether you are new to solar cell simulation or looking to enhance your understanding, SCAPS 1D provides an intuitive platform for exploring the electrical characteristics and efficiency of solar cells. Subscribe to my channel for more tutorial and in-depth guides on using SCAPS 1D effectively. Let's dive into the world of solar cell simulation with SCAPS 1D. So here is the environment of SCAPS 1D software. We can set up the temperature, voltage, frequency, and number of points. Similarly, we can enable or disable the series resistance and similarly the shunt resistance as well. For the simulation of today, I'm going to disable them to make things simpler. Similarly, using this button we can perform the simulation of the structure under dark conditions and also under light conditions. And then over here we can specify the spectrum file. For example, here I'm using AM 1.5G under one sun conditions. So we have the choice of choosing a spectrum. We can choose a single wavelength. For example, here you can see the wavelengths are like 300 nanometers, 350. Here are different options. Or we can select AM 1.5D or AM 1.5G. The difference between AM 1.5D and AM 1.5G is that AM 1.5D only simulates direct spectrum, while AM 1.5G simulates direct plus diffused sunlight spectrum. So here are our different choices. The solar spectrum typically extends from the infrared to the ultraviolet region, with wavelength ranging from 0.2 to 3 micrometers. But the intensity is not uniform. The path length of the light in the atmosphere depends on the angle, which will vary with the time of the day. And this is given by the air mass number, which is secant of the angle between the sun and the zenith, or you can say vertical axis. AM0 represents solar spectrum outside the Earth's atmosphere. Similarly, AM1 is when the angle is 0 to the vertical axis. Similarly, AM2 is when the sun is at an angle of 60 degrees to the zenith. Similarly, AM 1.5 is when the sun is at an angle of 48.2 degrees. So generally, there are some standard test conditions under which we perform the measurement, or you can say the characterization of solar cells. And these standard test conditions are room temperature 25 degrees C, AM 1.5 spectrum, and a light intensity of 1000 watts per meter square, which converts to 100 milliwatts per centimeter square. So the program has already chosen AM 1.5G, which is the correct form of spectrum that I want to use for the simulation of this structure. And the incident light intensity, we have control over it, but we are going to keep it at standard test conditions. I'm interested in looking at the current voltage characteristics and quantum efficiency of my solar cell. So I'm going to check these two tabs, and I'm going to run a sweep from 0 to 1 volt for the silicon solar cell. And you can change the step size or the increment, and I want to stop the simulation after we arrive at open circuit voltage. Similarly, for the quantum efficiency, I want to run a sweep for the wavelength axis from 300 nanometers to 1200 nanometers. At this point, we have to create the structure for the solar cell. So for the structure, as I already told you, that we want to work on a PIN structure. Matching with the previous Silva-Cotticat simulation of the silicon PIN solar cell that I performed. So let us first define the p-type layer, and I'm going to name it as p-type silicon. Let me be a little slow. So in order to add this layer, we click on add layer, and then I'm going to name it as p-type silicon. I'm going to keep the thickness. You have options over here. You can set the thickness in nanometers as well. For the p-type silicon layer, I will set the thickness to 0.5 micrometers. Here we have to enter different parameters, material parameters for silicon. So band gap for silicon is approximately 1.1 electron volts. Similarly, electron affinity is approximately 4.05. For silicon, the dielectric constant is 11.7. Density of states in the conduction band is 2.8 E19 per centimeter cube. Similarly, density of states in the valence band is approximately 1 10 to the power of 19 per centimeter cube. The electron and hole thermal velocity, let us keep the same values. The electron mobility for in silicon is approximately 1500, and the hole mobility is approximately 450 centimeter square per volt second. It's a p-type silicon layer, so I'm going to set the n-type doping at 0, and I will set the p-type doping to 5 into 10 to the power of 18 per centimeter cube. Similar to the Silvaco TCAD structure that I previously simulated. So we have already defined different parameters for the p-type layer. Let me double check them. They look okay. We can also define the OJ hole capture coefficient and the electron coefficient. So let me set it to like a low value of 1 minus 20 for the hole coefficient, and similarly for the electron capture coefficient as well. And I will keep the radiative recombination coefficient at 1e minus 1/8. We also have the option of including defects over here. Like for example, you can introduce the defect type and the capture cross section and the number of defects, etc. But in order to keep things simple, I'm not going to add any kind of defects. And then you can set the absorption for the silicon layer from either using a file, like for example here it directs you to a folder where we have absorption spectrums for different materials. So you can use and then we have this absorption file for silicon. For materials where you don't have any absorption files, you have to create them. But I'm going to use the absorption from model, and you can see here is the model. So now that I've set all the properties of the p-type layer, I'm going to add this layer, and now you can see the first layer is added. It's a p-type silicon layer. At this point, I'm going to introduce the I layer for the structure as well. Let me label it as I layer silicon, and I will keep its thickness at 10 micrometers, and then we specify different material properties for silicon once again for this layer. For the I layer, similar to the Silvaco TCAD simulation, I'm going to set its doping level to n-type 1 into 10 to the power of 14 per centimeter cube, and I will set the p-type doping to 0. So let me double check these parameters for the I layer. 10 micrometers, 1.1 energy band gap, electron affinity, permittivity, density of states in the conduction and valence band, velocities, electron and hole mobility in centimeter square per volt second, and similarly the doping concentration in the I layer. So we are going to add this layer as well. So click on add, and now we add our final layer, which should be n-type silicon. So the layer thickness is 0.5 micrometers, and its band gap is 1.1. Electron affinity of 4.05, dielectric constant 11.7, density of states in the conduction band and valence band, the electron mobility and the hole mobility, and I will set the doping to 5, 10 to the power of 18 per centimeter cube, and I will set the hole doping to 0. And we have chosen the absorption from the model option over here. You can choose absorption file as well over here, so you have that option. Let me double check the parameters for the n-type silicon layer. Looks fine, so I'm going to add this layer. Now you can, so this is my left contact and this is my right contact, and light is incident onto the sample from the right contact, which is the n-type silicon layer. I can also set the properties of the left and right contact by clicking on this tab. So like here, instead of the flat bands, we can enter any metalwork function, but I'm going to keep things simple, so I'm going to use flat bands. Click on OK. Similarly, you can do the same for the right contact as well, and I'm using flat band. But instead of that, you can use a metalwork function as well. I'm going to save the structure for future use as well. So at desktop, I've created a folder. Where is the folder? Here is a folder, and let me name it as silicon PIN 10 micrometers, and the extension would be .def. I'm going to save the structure and click on OK. So now our structure is saved. As you can see over here, so click on OK. And in order to run the simulation, we click on calculate single short. So I click on that. The voltage is ramping up from 0 to open circuit voltage. Now the wavelength is ramping up. The simulation has been performed by now. In order to look at the current voltage characteristics, I click on I-V. So here are my current voltage characteristics. My open circuit voltage is 0.5154. The short circuit current density is 34.4516. Fill factor is 80.71. The efficiency is 14.33. Similarly, we can look at the quantum efficiency curves as well. So I click on this quantum efficiency tab. Here is my quantum efficiency. Like this is the internal quantum efficiency. So now what I can do is I go back to the IV characteristics, and you also have control. You can choose between log file and log and linear vertical axis. Also, there is a way to show the data. So I click over here on show. So this shows me the data, the open circuit voltage, short circuit current density, fill factor, efficiency, maximum power point for voltage and for current density as well. And here is my voltage, total current density, recombination generation, bulk, etc. So what we can do is we can also copy this data by using Control plus C option, and we can plot it in origin, for example. So I go to origin, and I use Control plus V option to paste the data, and here is my voltage axis and here is my current density axis. We can enter the unit as well. So we choose these two columns, and then we click on line plus symbol, and now here is my curve. So similarly, you can like show the other options as well, lines plus ticks. We can show the top axis and the right axis as well. Hit on apply. And we can change these names and we can enter the units as well. But the point here is to tell you that we can plot the data as well in Origin software. Don't want to save the project. Okay, so these are the IV characteristics for the silicon PIN solar cell. Now, by clicking on action, I go back to the main window. And now at this point, what I want to do is I want to perform the simulations for 3 different structures, 3 different silicon PIN structures. One with an eye layer thickness of 10 micrometers, another one with an eye layer thickness of 20 micrometers, and a third one with an eye layer thickness of 50 micrometers. So instead of performing, instead of like creating separate structures for each one of them, what we can do is we can go to batch setup and we can add a layer over here, and I want to vary the eye layer thickness. So from this drop down menu, I select eye layer silicon and the unit is micrometers, and I click on custom list and then click on set. So here I set the eye layer thicknesses to 10 micrometers, 20 micrometers and 50 micrometers. And then I click on update. So all these 3 values are updated. Then I click on update and OK. So these parameters have been saved. And then I click on OK once again. So then I click on record setup, and from here I want to look at the IV characteristics. So I click that option and click on insert above, and then click on OK. And now to look at the results, I click on calculate recorder. So the simulations are running now. Okay, the simulations are finished running. So now you can click on recorder, and here you see different results. Like for example, here is the efficiency of the silicon PIN solar cell as a function of the eye layer thickness, where we have 3 points: 10 micrometers, 20 micrometers and 50 micrometers points, and the efficiency is decreasing as a function of is decreasing with increase in the eye layer thickness. It's decreasing from 14.33% to approximately 14.327%. Similarly, from this drop down menu we can also look at the open circuit voltage. The open circuit voltage is increasing with the increase in the eye layer thickness. It's increasing from 5.15 to 5.1, from 0.515 to 0.517. Similarly, we can look at the short circuit current density. It's decreasing as a function of increase in the eye layer thickness. The fill factor is decreasing. The maximum point for voltage and current as well. So let us look at eta. Similarly, we can also see the results over here as well. Here are all the results, and we can just copy these values and we can plot them as well. Like here is the thickness: 10 micrometers, 20 micrometers, 50 micrometers of the eye layer, Then we have the efficiency column and the open circuit voltage column, etc. Short circuit current density. So you can just copy the data and you can paste them in origin and you can plot them. Now let us perform a comparison of these simulations with the Silvaco-TCAD simulations. So let me direct you to that folder. Here are the Silvaco-TCAD simulations of the 10 micrometer silicon PIN structure. Here are the doping levels, the structure, the meshing, the energy band diagram. Similarly, this is the photo generation rate for the structure, the photon absorption rate. You can also see the photo generation rate and photon absorption rate from here as well. Energy band diagram under light condition. Here are the IV characteristics of the silicon PIN solar cell at an eye layer thickness of 10 micrometers. So we can see the IV characteristics under both dark and light conditions over here, and then here is the power curve, and then here are the figures of merit for the solar cell. So I have compiled them into a single slide. Here are the figures of merit for the silicon PIN solar cell for an eye layer thickness of 10 micrometers. So now let me compare it with these results. So like for example, let's talk about the efficiency. So if you are using SCAPS 1D software, the efficiency is decreasing as a function of or you can say the efficiency is decreasing with increase in the eye layer thickness. However, if you are looking at the Silvaco-TCAD results, the efficiency is increasing in this thickness range. Similarly, if I look at the open circuit voltage, and also like let us double check the values as well. The efficiency is approximately 14.3% if you are using SCAPS 1D software. However, if you are using Silvaco-TCAD software, there is an increase in the efficiency from 17 to approximately 21% if you are increasing the eye layer thickness from 10 to 50 nanometers. Now let us look at the open circuit voltage. The open circuit voltage is increasing from approximately 0.515 to 0.517 with increase in the eye layer thickness in SCAPS 1D. And if you look at the Silvaco-TCAD simulation, the open circuit voltage is close to that of the SCAPS 1D software. However, it has a decreasing trend with increase in the eye layer thickness. Now let us look at the short circuit current density. It's decreasing with eye layer thickness, and if you look at the Silvaco-TCAD results, it has increased from 43 to approximately 58.86 centimeter, so milliamps per centimeter square. So these are quite like different results as compared to that of SCAPS 1D software. You can also look at the fill factor decreasing from which has a decreasing trend, but generally it's around 80%. Now if you look at the Silvaco-TCAD results, the fill factor is approximately 75 for 10 micrometers eye layer thickness, then approximately 74 for 20 micrometers, and approximately 73 for 50 micrometers. So what I mean to say is that the results of the simulations of these two softwares are not the same. So we click on action to go back to the main window. So the accuracy of solar cell simulations depend on several factors, including the specific applications, the models used, and the validation against experimental data. Both SCAPS 1D and Silvaco-TCAD are widely used in the field of solar cell simulations, but they cater to somewhat different aspects and approaches. For example, let us first talk about SCAPS 1D. SCAPS 1D is well known for its ease of use and its focus on capacitance-based simulations. It is particularly strong in simulating the electrical characteristics and performance of solar cells, such as IV characteristics, efficiency, and carrier transport. But one of the limitations of SCAPS 1D is that it may lack some of the detailed physics and advanced device modeling capabilities that we can find in more comprehensive tools such as Silvaco technology computer-aided design. Silvaco TCAD offers a broader range of simulation capabilities beyond just solar cells. It can cover other devices, and it can include more detailed physics-based models such as advanced carrier transport, quantum mechanical effects, and detailed process simulation. The Silvaco TCAD can be more complex as compared to SCAPS 1D, and its accuracy heavily depends on the specific models and parameters chosen for the simulation. So therefore, the choice between SCAPS 1D and Silvaco TCAD depends on the specific requirements of your solar cell simulation project, the complexity of the device you are studying, and your familiarity with the tools. For basic solar cell simulations focusing on IV, I would say SCAPS 1D may offer a more straightforward approach, but for more complex simulations requiring detailed physics modeling and process effects, Silvaco TCAD would likely provide more comprehensive capabilities despite its higher complexity. So, in order to perform the simulations, you have to look at the pros and cons of these two softwares, and then plan ahead with performing the modeling and simulation of your research, and that may lead to experimental approach and performing different experiments, growth of your solar cell, then characterization, optimization of your individual films of the solar cell, and then optimization of the fabrication process for devices, and then device characterization, and this process continues. I hope this session was useful for you. I will come up with more SCAPS 1D based simulations like perovskite solar cells and other kind of solar cells as well, and I'm going to compare them with the Silvaco TCAD simulations of those structures as well. Until next time, happy analyzing your solar cells with SCAPS 1D software. Take care. Talk to you next time. Adios.